I'm talking about massively parallel finite element simulations in deal.II. deal.II is an open source finite element framework, and I'm telling you what I did together with these colleagues. Carsten just introduced me. And what we did recently was taking this finite element library that is used in all kinds of applications and make it scale to a huge number of processors. And so let's start. Don't really need to go into that. So before I start why that's important, I have one numerical example that I wanted to quickly show, which is the convection in the Earth mantle. We are living on the crust here. There's a core, and everything between is the mantle. It consists of, mostly solid rock that is slowly moving and deforming due to temperature differences. And if you want to simulate this, then here's an example of a 2D visualization of a certain time step. And so the coloring is the temperature. That's symmetric here. On the right, you have your adaptive mesh that resolves the small plumes and local features that are in the solution. And so that hopefully demonstrates the need for adaptive mesh refinement, especially if you go to 3D. And another thing is that the equations are really complicated. You have all kinds of quantities you want to track, material properties, and so on. So it's a very complicated system. And on top of that, even with adaptivity, you end up with a huge number of unknowns. And so you need a cluster to solve these kind of problems. So the goals here are finite elements on adaptive mesh refinement. And we want to go to 10,000 or more cores and billion unknowns or more. The goal is to, we implemented this in the library deal.II, and so it's flexible. You can use it for all kinds of problems. So I didn't want to write a code to solve Mantle convection problems, but what I'm doing is I'm extending the library so that all kinds of people can use that. So you can use higher order elements, all kinds of coupling between equations, and whatever you want to do. And fourth thing is I want to reuse software, so I'm not doing the adaptive mesh refinement and coding all this stuff up by myself. We come to this in a second. And fifth thing that I haven't listed here is you want to abstract the not so nice details about parallelization from the users. I don't think you can totally abstract this away. You cannot let the user access data that does not exist locally on your processor, but you don't want the user to write MPI commands all the time. So that's also important. Okay, our process, what I'm talking to you today, is published in that paper if you're interested. And I guess in this audience, I don't really have to tell you what you need to scale to a large number of processors. But I think three things are very important. The first thing is you need to distribute your data storage. In the talks before, that was also already mentioned with Samurai, the talk before, for example. You need to have algorithms that do not depend on the total problem size. You cannot just copy the whole solution vector to processor 0 and do some computation there and hope that works. And the third step is obviously that communication doesn't scale, so you need to avoid global communication by doing point-to-point stuff as much as you can, and hide communication behind local computation. Okay, not much magic here. And so in deal.II, before we started, and I guess it's the same thing in many other libraries, so it was already a parallel code using MPI, and we're using a package for the linear algebra part that is split up and scaling nicely. But everything else was the same as the serial code. So the mesh and all handling of the unknowns, degrees of freedom, and everything else was duplicated between the processors. All the work was duplicated because of that reason. And so what you end up with, it works reasonably well if your problem doesn't get too big so that you cannot store the mesh locally, or as long as the number of cores is small enough, then it's working. So, but we want to do better. Okay, so if you look at what basic blocks a finite element software is made of, it's pictured here with the with the names that are standard for the deal.II library. You have stuff that is independent of parallelization, that is the concept of unit cells, of the finite element spaces, quadrature rules, mappings, and so on and so on and so on. You have shaded in gray parts that are influenced by parallelization. So that's what in deal.II is called the triangulation. That's the mesh with all the associated data. That is hard to do. You need to distribute the mesh. You want to do adaptive refinement. You want to rebalance stuff, and so on and so on. The second part is the handling of the unknowns. So in each cell or on interfaces between cells, you have unknowns depending on your finite element type. And you need to number those and handle neighbors and neighborship relationships between different processors. Number 3 would be the linear algebra. That's pretty easy to do. You use an existing library like Trilinos or Petsy. We have both interfaces in deal.II, and you just use these objects, and everything else happens, preconditioners and everything. I mean, there's no perfect preconditioner, but you cannot be better than these libraries that exist for tens of years with hundreds of man years of work in there. Okay, and then there's all the minor stuff that needs to be done in parallel, and that might become a problem if that can be a bottleneck if you have 10,000 processors, so the rest of your program is 10,000 times faster, and then suddenly some kind of part of the application dominates. So that's all kinds of stuff. I don't really want to go into detail. What you have to do there basically is you do local work and then do some communication to add up with your global result. Okay, so for the meshing, we're using the pforest library that was introduced in the morning or earlier today from Carsten, and Toby also talked about this. And the basic concept for those who weren't here is you have a coarse mesh, which is here made out of 3 cells, and you want to refine those in 2D into 4 children, and in 3D into 8. So it's a quad or an octree that is rooted in each coarse cell. And what this library basically does is it only stores the refinement flag. So it's just a flag saying, well, this cell is refined, and then these children are refined, and so on and so on. And this is handled in parallel and scalable and very efficient, and so on and so on. And underlying it is space filling curve approach. And so this mesh here with this space filling curve matches to this tree. Okay. And so how do we go about doing a finite element simulation with that? So as already mentioned earlier, in this approach, the partitioning between the processors is very easy. You have the space filling curve, which is just a list of cells that you have, and you cut this into equal sized pieces. So here, for example, you have your 7 cells, and you cut this here, and you have the first 4 cells go to the first processors, and the next 3 cells go to the other processors. Okay, that is what pforest is doing. And now comes the point that we need all the information in the deal.II mesh. And so what we are doing is we are recreating the standard deal.II mesh you used in a serial application, but we only create those cells that are local, that are our own cells. And the advantage is that all the parallel handling is only done with this refinement information, and only for our local cells where we need to do the computations, we have this rich data structure. We really create all these cells and the hierarchy and all these vertex coordinates, connectivity, faces, material indicators, and all this kinds of stuff that you have attached to your cells to do your computations on. And, how does it work? Well, pforest has a very small interface. Carsten explained that. And so you basically query it and ask, well, is this cell, is there one of my cells in there? If yes, okay, I refine my cells, and I ask pforest again, is my cell somewhere in there, and so on and so on. And you also need to create a ghost layer for your, I'll show that on a picture, one layer of cells around. So this example is a simple unit square. It's divided, it's adaptively refined, and it's divided between 3 processors in red, yellow, and blue. And that's the view, that is the local deal.II mesh that is created from this view. And so each processor has their own cells, one layer of neighboring cells, so it knows how the connectivity is to the neighbors. And here are a few core cells that that get created because we start from the same coarse mesh and we have, again, a 2-to-1 balance for the finite element computation. But these are, we call them artificial. They are colored here in white. They are not used for the computation. And they are a small overhead compared to the real computation. Okay, so that's the meshing. And now we have the problem. In finite elements, you have your unknowns that live somewhere on your cell. For a simple linear finite element, you have, on each vertex, you would have one unknown. It's obviously more complicated. You can have unknowns in the inside, on the faces, and so on and so on. And what you need is you need some kind of global numbering from all these unknowns. You could say, well, I can avoid that and just do local numbering, but you need some way to identify that if this belongs to one processor and this other cell to another processor, if they need to know when they talk about this degree of freedom that it is the same. So they have to have a unique naming somehow. Okay. And so the sketch on how to do that, this is non-trivial because we don't know the whole mesh anymore. So we cannot just loop over all cells. We did that before, but that doesn't work anymore, of course. And so very simple sketch on what we're doing is, the first thing is I decide on ownership for the degrees of freedom. This is later on reflected in the linear system. So 1 degree of freedom corresponds to 1 row or column in your linear system, your global system. And so this ownership determines who owns the row of that matrix in your linear system. And that's arbitrary. Here I did it by writing the number in one of the 4 cells. And you can do this without communication. And the next thing is everyone enumerates the own degrees of freedom. That's easy. That's same as the serial code. You just skip the ones that you don't own. And then you have to shift them to make them globally unique. And for that reason, if I'm processor 2, I only need to know how many degrees of freedom does processor 1 have. I get one number and I can shift my indices and I'm done. And then I need to know about the indices that are not mine but that are of my interest. To give you an example how that looks like, so these are 4 cells and 4 different owners. So first thing is we do the arrows point to who owns that degree of freedom that's again on the vertex. So the first thing is local numbering. Okay, so the red has 0, 1, 2, and 3, and the others only have 2 unknowns, which is not very well balanced in this case, but normally you have a few more cells. And this is again the picture we had before. And the next step is, okay, these are 4 unknowns, so we need to shift the 0 and the 1 on this processor by 4. And so now we already have our globally unique ordering or numbering. And the problem is now that, of course, the green processor, for example, needs to know that this is 4 and 5. And how do you do that? Again, the picture on top is the one that I had before. And so in a step here, this is now the view from the green processor. So it doesn't know that here's 1 and that here's 3. It doesn't need to know about 0 and 2. It doesn't even know what cell is there. But this would be in the ghost layer. And so blue would send 9 and 8 to the green processor, and so then the green processor knows about those and also gets the one from yellow. But the problem is, for finite element computation, you also need these degrees of freedom on the green processor. So you need really 1 layer of cells. It's not immediately obvious that you need that, but you can think about if you want to compute something like an error indicator, you need a gradient approximation on this ghost cell to know if this face here has a large gradient jump, for example. And so you want to know that too. And so how do you do that? Well, you need to do a second computation step because yellow doesn't know yet about 1 and 3, but in the same communication step, it gets it from red. But all this communication is happening all at once. So each processor is sending all the knowledge only to its neighbors, only to its few neighbors that are like 20 or so for a run with 10,000 processors. And then there needs to be a second route of communication, and then we're done. Because in the first step, red sends to yellow, and in the second step, then yellow knows everything, and then it can send it to green. And so that's here. So the second transfer, and now green is happy and knows everything. That's just an example on how an algorithm gets a lot more complicated if you want to have it scalable. Okay, so that was handling the numbering of degrees of freedom. That works in a, yes?
I'll use the mic. So is this what you just described, linear in the number of processors, as in as many communication steps as there are processors?
No, it's exactly 2.
Okay.
So you need one layer of cells around your own cells, right? And in the first communication step, the owners of these cells get all the information they require. And in the second step, they can send it to me. So it's always 2 steps at most.
But how does that, maybe your previous figure, how does the blue one know that he's 8 and 9?
Oh, I'm sorry.
Until things have been summed up all the way across.
You were asking why does blue know that it's 8 and 9? There's one global reduction that every processor then knows how many unknowns every other one has. But that's just one number that needs to be sent. Yeah, exactly. So that's not done in a serial fashion one by one, but everything is done at once. And you can do your local numbering, so the communication is hidden, you do your local numbering. You need to fill in these indices that you get, and doing that, you can already send out your cells to your neighbors. So that's everything is interleaved there. And that scales very well. Okay, when we're done with that, we can just do the standard finite element way. So you assemble your linear system. And as I already said, you split up your system row-wise. That's the standard approach for sparse linear systems if you want to do that in parallel. Again, you can use a library like Petsy or Trilinos. And so you loop over your own cells. You have your cell contributions. You write them into your local part of the matrix. And all this communication is, again, only to your few neighbors that own these degrees of freedom of rows that are not quite yours. But that's all hidden in that library, so there was no implementation that needs to be done. And of course, then you need to have parallel solvers and preconditioners and so on and so on. But I don't want to discuss that here. Okay, a few things I explained a bit more simply than it really is. So I just want to list stuff that is a bit complicated that I haven't talked about. Error estimation is an important part if you want to do adaptive mesh refinement, of course. You can do the error estimation locally if you have your solution at least on your own and on your ghost layer. That's okay. But how do you figure out which cells to refine? That's a hard problem. You don't know which processor owns what and where the error is what. So in a serial program, you would just take your error indicators, you sort them, and you take the biggest error indicators and refine them. In parallel, you have to do basically a parallel bisection to figure out at what level or how many cells do I need to refine to get a certain error. That's a bit more complicated. There's a typo in there. That's what I said. Of course, if you do this octree-based refinement, you have hanging nodes. You have to deal with the hanging nodes. And you get in your linear system, you get constraints that some values depend on a linear combination of other values. So you have constraints, and these constraints might form small chains. And you have to be careful to do this correctly, that all processors think about the problem the same way and have the same constraints, at least the same constraints on these cells where they need to know it. So that you need to know all the constraints on your own cells. You also need to know the constraints on the ghost cells to do the transfer correctly, but you don't need to know about everything else. So that's, again, localized all the computation that you need to do. Okay. And of course, you need to, if you do your adaptive mesh refinement cycle, you want to transfer your solution. So you need to pack your solution. And this is done by pForest, basically. We attach stuff to the cells that come from the finite element solution and tell pForest, okay, please rebalance everything, and they ship the solutions, and then we unpack the stuff and put it back into the solution vectors. So that's also, point-to-point communication mostly. All right. With that, that's what I wanted to show about this. So I'm going to show some numerical results, just to show that you can run on a larger number of processors than was possible before. So that's the fixed problem size of 300 million unknowns. That's a very simple 2D adaptive refinement on a unit cell, just a Poisson problem to see that it works. So that's 120. So that's the number of processors on the x-axis and the wall time on the y-axis. So the best thing you can hope for is this linear scalability. And you see, I don't really want to touch everything here, but all the components scale linearly pretty nicely. Well, not the solver up here, but you see that the problem size gets very small on the right-hand side. And so you cannot expect a linear solver to scale with a small number of unknowns. So that is, the red line here is less than 100,000 unknowns per core, which is not a lot, especially for a simple problem where there's not a lot to do. Okay, here I have a fixed number of processors, and I increase my problem size. You can see that we can go to, that's 1 billion, so it's a bit less than 1 billion in this case, but yeah. And again, the best thing you can hope for if you double your problem size is that your solution time doubles, and that's, again, the linear line there.
So this weak scale starts with 512 processors? Or?
No, sorry, that's maybe a bit bad notation. It's a fixed number of processors, and I increase the problem size. I think that's not the right notation. I think I should have done it in a different way, but that's what I have. One thing I talked about was distribute all the memory. So you can look at, you increase, so that's now the correct weak scaling. So you increase your number of processors from 8 to 1,000, and you increase your problem size from 4 million to 500 million unknowns. And so that's roughly 500,000 per core, and you see that the memory is more or less constant. It's not exactly constant. It's kind of hard to match an adaptive refinement to have a certain number of, you want to have, from here to here, you want exactly twice the number of cells, and it doesn't add up exactly. So that's why it jumps around a bit. Yeah, but that's pretty nice for a very, very large change in problem size. You see that everything important is distributed. And to make an example here, this is how the memory looks like from going from 1 to 500 cores, scaling the problem by a factor of 500. And you can see that, so that's the pink one is the memory that P4S needs that grows by a small amount. That's not surprising. It's, again, adaptively refined, so you get more hanging nodes, you get a deeper tree, you get, so there's some complexity there that increases, but it's a very small increase for a factor of 500 in the problem size. And so the deal.II triangulation, so that's the mesh that is created on each processor only for the own part. It's also increasing a bit. Again, it's a deeper hierarchy, so you have a few more artificial cells and so on. But it's, again, a factor of 500, and the increase is just a couple of %. The big chunk is the linear system, so that's the system matrix, and this is like 2 or 3 vectors. That's, again, a very simple problem. If you have higher order or if you have a coupled problem with several unknowns, then that chunk is obviously bigger. Interestingly enough, the matrix gets smaller. This is due to more constraints, more hanging nodes, and so less entries per row because of the constraints. That's kind of funny to see that. Again, it's hard to have exactly numbers. Okay, and so coming back to the Mantle convection problem, very quickly, I don't want to talk about this. It's basically a variable viscosity Stokes problem coupled with a temperature equation. And so I have some results. You can see here, it looks similar to the pictures Carsten showed. So that's isosurfaces of a temperature, and this is a mesh colored, how it is distributed between processors. That's with 50 million unknowns. I have some scalability. That's actually in 3D and a very small problem. Well, small, relatively small, with 4 million unknowns. But again, it's a more complicated coupled, higher order, whatever. You can see, again, the linear scaling up to 1,000 processors, all but the preconditioner construction and the solver that does not scale because the problem gets very small. And, yeah, similar 2D, increasing the number of unknowns. And with that, I'm done.
Thanks, Timo. So we have
questions. What is a quick condition?
Okay, yeah, I didn't talk about this because it's not really the focus of what I'm doing. We use algebraic multigrid mostly. So for this coupled system, so you have a block preconditioner, and for each block you do algebraic multigrid, which might be Trillinos ML or Hyper through PETSI, whatever you like to do, or something else. No, we do not. That's a limit. The question was, what do we do if the coarse mesh is too big? Well, that's a limitation of P4S, basically. And it's a question if that's really useful. This framework is made for adaptive mesh refinement. And so if your coarse mesh is very big, the question is, can you really do a lot of adaptive mesh refinement? So that's a separate question. You could think about how you would extend this, but currently, no. The coarse mesh lives on every processor. For example, in this thing, you have like 6 or 8 core cells, right?
This is just a remark to the space-filling curve approach. Yeah? If you have a coarse problem and you want to solve this in parallel, then you need an extra distribution for this, because the space-filling curve makes a good distribution of the surface mesh, but then the distribution of the coarse meshes may be very unbalanced.
I'm not sure I understand your question correctly. Are you asking about geometric multigrid, or?
In geometric multigrid, you have this, but always if you have a coarse mesh, then you need a good distribution for this also. Yeah?
Well, okay, the question was, what's the good distribution for the coarse mesh? Yes, it's hard. You cannot just chunk it up because your problem might be just in one corner where you adaptively refine, so you need to move coarse cells over too. Yeah, so that's hard to do. But, well, we have the coarse mesh on every processor, which is a limitation, I admit, but so we don't have that problem.
The coarse mesh is still equally split between processors, just that it's just very few, I guess, per processor in the end. I would have been interested in kind of a rule of thumb, how much time you spend on meshing, on setting up matrices and solving maybe setup of the AMR, the right multigrid solving operation.
Okay, the question was about what part of the program, how much time to spend. First, of course, it depends. It depends on your problem. Let's see. Yeah. So, we can take a look at it. And here you can clearly see, there's this logarithmic scaling for the time, and you can see that the linear solver just dominates everything. And so let's look a bit more exactly. So the blue line here, that is the stuff that is related to mesh refinement. And so that's much cheaper than assembly, which is the blue part, which is the assembly of the Stokes problem. So you have one order more expensive is the finite element assembly, and one order more expensive is the linear solvers, as a rough rule.
The linear solver would contain setup of the multigrid.
Here that's separately. Here that's the black line. That's the construction, which is cheap as long as you have big enough problems locally. Otherwise, it explodes. Yes. The question was, local adaptive refinement creates an imbalance. What do we do about it? Yes, for sure. So this is a time-dependent problem, and every few time steps I evaluate error indicators, decide which cells to coarsen and refine, do this, and then call into P4est and do a complete rebalance. So we rebalance perfectly again, and the same number of, or roughly the same number of cells end up on each processor. That involves, of course, sending the solution over to that from processor A to B, and possibly sending the solution completely to the other. It might happen if you refine somewhere that basically every ownership moves around. But that's actually okay and works surprisingly well, because it's point-to-point communication. You don't collect the stuff. You know which processor gets the information, and it can all happen at the same time. So it's not really expensive. And so we do the rebalance, and P4S does not try to keep the domain roughly on the same processor, but it just does the new space-filling curve, splits it up, and just sends the stuff over. And we do that every couple of time steps, and that's included in this line. So that's this line here. So it's very cheap.
Do you have periodic conditions in deal flow?
Do you mean what?
Periodic conditions.
Periodic boundary conditions.
Yeah.
In the distributed case, I think nobody tried it out yet. But in the serial case, yes, I would have to check.
There are no urgent questions. We should stop here. It's 12:30. So thanks, Timo. Thanks all the speakers. And I'll see you next year.